Yeah, the beeping is the door doesn't understand why it isn't opening. So that's why it starts yelling like that. And I guess with that sound, it must mean class must be starting. Ladies and gentlemen, welcome back. Ears open, eyes wide. Let me go ahead and get started here. Before we get into what I want to get to, some of the morning announcements that a couple of you asked questions about this. First, for those of you who got here early, I left a quick question for you to give me a Lewis structure for that right there. And so I'm only going to give you like 30 seconds to do it. Shouldn't take too long. The only reason I'm only giving 30 seconds is just because, well, we're about to shorthand this fairly quickly here. But if you haven't a chance to do it, well, you got 15 seconds to do it. All right, good. That was 30 seconds. So if you felt like you missed out on something, you really shouldn't have. This was problem 2.2b in the book, so that shouldn't be a big deal there. Right. So with this, for a Lewis structure, remember how to write these out is you have to kind of keep in mind of what atoms go to what. As a reminder, a few things we talked about last time, halogens are monovalent. So those three chlorines are only going to be attached to that carbon on the left. And that carbon on the left is going to be attached to that carbon on the right that has the rest of the carboxylic acid. So what I'm expecting is something that looks like this. So Cl, C, Cl, Cl, C. So you have that first. There's the CCl3, and then there's the carbon there. And then O2H. So probably, now remember, so O2H, you have to be mindful of how that's set up. Hopefully if you read ahead, you realize that this is actually carboxylic acid, so it should look like this. And again, if you're wondering why wouldn't it be, or what if it was anything else, if you check the formal charges, you'd realize that the formal charges wouldn't be sufficient. And so that's something like that. It's crummy drawing real quick there, but there you go, there's what it is. All right, so that shouldn't be too bad, so that was that. Right, so, all right, so I know a couple of you already asked this, but I kind of blew you off so I could talk about it all in person, or all as a group. Good news is that I finally released your homework for Chapter 1 today. I do apologize for being so late. That was on me. I'm going to have Chapter 2s. I'll be able to work on Chapter 2s today after class, pending any sort of disasters happening. But just very briefly, let me explain. So normally I would have, in theory, I would have all the chapters out and available at the beginning. I'm going to be working on that probably throughout the week. I'm hoping to actually have all of them done, or have every chapter out by the end of this week, just so you guys have them already. So let me explain how this works, because it's not explicitly written, so just make sure we get the idea here. So there's 20 questions for a total of 10 points. So you can do the math on how much that is. Normally, as I mentioned before, normally I would have them do a week after I cover the chapter, but since I've already covered Chapter 1 and I just released it today, for this particular chapter, for Chapter 1, the due date's already on there, but it's going to be due 2 weeks from today. So whatever date that is, I don't know. I think it's the 1st. So there you go. So there's that. The 1st, 11:59 p.m. The way I do it is you get 5 attempts. Is that I made 5 attempts. No penalty on those attempts unless you exhaust all 5. Then it's wrong. Can you do it late? Yes, you can do it. Actually, before I get to the late bit, keep in mind that even though I say 5 attempts, I'm under the assumption that if it's a multiple, that if the question that I have, because the questions themselves are like, draw a structure, fill in the blank, multiple choice, true or false, kind of the standard type stuff. I think it's safe to assume that if I pick the true or false question, you're not going to get 5 attempts on it. That makes sense. I'm not saying that to try to be funny. I'm saying that because I've gotten some flack about that in the past. Let's be reasonable here. With the multiple choice, same thing. I'm going to assume that even though it is a multiple choice and you get 5 attempts, chances are you probably actually don't. All right, so keep that in mind. Really, the 5 attempts are more for the filling in the blank, having to do long form answers, because obviously I know that for a lot of these types of programs, that certain ones, they only accept a particular format, And the last thing I need to be doing is losing points because you don't put it in the right format. Now after 5 tries, if you didn't put it right the first 4 times, I'm sorry. I figured you would ask me before that. You understand me? Okay, very well. So that's so understand that. So 5 attempts I thought was good enough. Now, back to what I was saying before, can you turn it in late? Yes, you can. Is there a deduction? Yes, there is. So there is a deduction of 25%. I didn't put this on your syllabus, so I'll update your syllabus to reflect this. I thought I did. But yeah, it'll be 25% deduction for up to 3 days. So essentially, you turn in 1 day late, it's 25% off. Turn in 2 days late, 50% off. 3 days late, 75% off. After that, don't bother. Well, because it's 100% off. So then why would you? So that's that. So like I said, so again, I apologize for the slow start with that, but hopefully you guys can get on that fairly soon. I think 2 weeks should be enough to do that, and at least the questions that I picked, or at least the ones that I looked at, mostly, in my opinion, mostly are Gen Chem review. What's the hybridization to this? What's the shape of this? How many sigma bonds for this, etc., etc. Nothing. It shouldn't be anything too crazy. At least I don't think so, but of course I'm biased. What can I say? All right, so we good to go? All right, I'm going to carry on then. The other thing too is this. I got this question a bit. Is what's the first exam going to cover? Which I don't know when their exam is. I have it written down, but I don't remember it. That's why I have it written down. It's supposed to be ideally, I wanted to cover chapters 1 through 3 in about half of 4. That's the ideal thing. All right, so chapter 4, what I mean by that, pretty much going up to, what's that called? At least through constitutional isomers and alkanes or nomenclature, or I don't want to talk about cycloalkanes yet. I mean, I might, but so just you want to prepare. So if you're trying to figure out how to mentally prepare yourself, chapters 1 through 4, just make it easy for you. And when we get closer, once I have a better idea of what we're doing, I'll make sure to give you a proper cutoff point. But I might as well have you guys study a little bit more now, because if it doesn't show up on this exam, it's going to show up on the next one. So might as well, heaven forbid, I try to over-prepare you for something. Right. Okay. Is there anything else? Now the clipboard doesn't tell me anything else that you need to know, so we'll just go ahead and proceed. Right. Now last time, as I've already alluded to, we had talked about how you can take a condensed formula and turn it into a Lewis formula. And I also mentioned last time, or last week, whatever it was, that at least in organic chemistry, there are certain ways to write this. And so we're going to talk a little more detail about that now, about what we call bond line structures or skeletal structures, depending upon what book you read. I'm just going to use what your book calls it. Right, so So we're talking about bond line structures here. What we're saying is, instead of taking the time to have to go through and, draw out everything that you've seen, well, that's actually a bad example, but there we go. So instead of having to draw everything out, you can actually shorthand it by using essentially lines in a squiggly line type manner to show the number of carbons that you have. So now here are the rules that you have to follow. If you don't want to write this down, you don't have to. This is page 53 where all this fun starts. But so first off, and I'm not going to write them down because they are in your book. 1, you have to make sure you draw all your carbon chain in a zigzag format. Okay? So if I'm going to have something, say something that looks like this, CH3, CH2, CH3, something that looks like that. The way you would draw that would just simply be something that looks like this. That's all. And so each point here corresponds to a carbon. So then this is a CH. Let me just do this. So this is a CH3 here. That's the CH2, and then that's a CH3. How are we doing? All right, good to go then. So the second thing is that whenever you're drawing, so the other thing that your book mentions here is that when you're drawing double bonds, ideally, you want them as far apart as possible. Again, it's kind of, I alluded to this before, but it's to try to keep in mind of what the shape of that thing is going to be. So what we're saying here is if you're going to draw carbonyl, for example, you know this. If you're going to draw, let's just say acetone, right? If you're going to draw acetone, which, you know, quick condensed Lewis structure looks something like this. If you're going to draw that, for example, ideally you should be drawing it like this, because you want to try to show off the fact that, hey, for this carbonyl carbon, what's the hybridization? sp squared, right, or sp2, or trigonal. Remember the shape of that's trigonal planar. Good to go? And so ideally, because you want trigonal planar, you want them as far apart as possible, in accordance with Vesper theory, ideally you want it to look like that. Please do not draw it like this. Okay? You don't want to draw it inverted like that. That's a party foul. Don't do that, please. Thank you. Okay. How are we doing? All right, very well. The next bit that your book mentions now is when it comes to drawing single bonds, the direction doesn't matter. And we're going to see this later. And I mentioned this previously, I forgot when, but I mentioned it, well, last week. I mentioned it last week that you want to be mindful. Yep. You want to be mindful that sometimes something may look different, but is actually the same thing. What I mean by this is if you have something, I don't know, just draw some ring here. So if I have something that looks like that, and then I have something that looks like this, or I have something that looks like this, or one more for the lulz, I guess. So you see all those, right? Those 4 things that I drew over there? Understand, I just drew the same thing 4 times. I literally just drew the same thing 4 times, despite how the lines may look, how things are bent. It's all the same thing. And we'll talk more about that in chapter 3, because like I've said before, the easiest way to know whether or not you've drawn the same thing or not, at least in my opinion, this is the easiest but also the longest way, is just to name them. And you'd see that all 4 of those things that I just drew all have the same name. Any questions? All right, very well. Now, this is where, what I was trying to allude to before, that example up top isn't good for this last one here. And that is, whenever you have an element that is not carbon or hydrogen, you have to write out the elements. Or as what your book calls them, by the way, and this is what generally we use, is that whenever you have an element that's not carbon or hydrogen, we call those heteroatoms. Because they're not carbon or hydrogen. That's really where it comes from. And so, like I said, this example here, well, you can kind of see it here too. Notice that for acetone, right, you notice how I put the lines and, just for, we know those are carbon, but for the oxygen, you actually have to draw that out. Because, understand that this, and say, this, if you look at these 2 things here, those are not the same. Okay? Those are not the same because they're not the same, so we'll just do that. And so because whenever you have something that looks like this one here where my pen's at, what that's telling you is technically there is it's not written of course, but there's a CH2 there, which is not the same as an oxygen. You understand me? Okay. And so like I said, for the top one, which I'll just draw, the way that this thing would look, again, it probably would look, as I said already, not the best example, but we only have technically 2 carbons. So the way you would draw that first is, well, there's my line. There's the 2 carbons. On the right-hand side, I have a carbonyl followed by an OH, so COOH. And then on the other carbon, I have 3 chlorines. So 1, 2, 3. It looks something like that. Those are CLs, by the way, sorry. For anyone, make note of that, or draw it better than I did. So how are you doing? You understand me? Pretty simple, pretty easy, I hope. Okay, good to go then. Let's make sure you're not lying to me. So one thing I want to make sure you understand is simply, if I give you a condensed formula, a Lewis structure, or later on, a name, you should be able to provide me a structure. ideally you should be providing me a line bond structure. Like I said, unless I specifically ask for a Lewis structure, these are the kind of cute little drawings that I expect, just because they're easier and it's organic chemistry once you get in the habit for it. Yes?
You just answered the question.
All right, very well. So yeah, so that's pretty much that. Because especially too, later on, as I've already alluded to a few times, and actually I've shown you a picture of this back in chapter 1, is that some of these molecules can get really, really elaborate and get really big. And so you trying to draw it as a Lewis structure probably would not be a worthwhile exercise. But okay. Let's see here. All right, so this is from 2.5. Let's do something easy here. All right, so practice problem H. It's draw a bond line structure for the following. Okay. All right, so let's break this down. So CH3, CH2, 6, OH. Right. So, again, there's many different ways to how to solve this, but for me, the way I'm looking, at least when I get started, when I first teaching kids this, what I do is make note of how many carbons are there?
7.
I'm hearing 6 and I'm hearing 7. There should not be a controversy with this number. Raise your hand if you think it's 6. Raise your hand if you think it's 7. Raise your hand if you think it's 8. Why would you say 8? That's weird. There should only be 7 because there's one CH3 and then there's 6 CH2s, right? 6 plus 1 is 7. How are we doing? So, that means at the bare minimum, the what you should be drawing there when it comes to those lines, it should be. Now again, the way you have to count it, this is important too, because a lot of students mess this up at the beginning, is that understand that even when, like anytime you draw like a line, that counts for 2. That's 2 carbons, not 1. Because this right here, like I showed you before, this right here, this actually, oh Jesus, that right there is a carbon. So be mindful when you do that. So count to 7. Now again, just do zigzags. I just do the easiest 2, 3, 4, 5, 6, 7. Is that 7? 1, 2, 3, 4, 5, 6, 7, 6, 7. Yeah. Okay. Have I lost the room yet? No. I hope not. Now, the last bit there is an OH. And so because that's not a carbon and a hydrogen, that's an oxygen, or i.e. a heteroatom, then we have to include it at the end. So yes, it does matter where you put it, because when I'm saying CH3, CH2, 6, then that means that that after this terminal carbon here, there should only be 6 carbons of CH2s. I just saw a hand shoot up. Go.
Yeah, I read in the book that each point represents 1 carbon bonded to 1 hydrogen. Could that be to multiple hydrogens, or is it just 1?
I want to make sure, I have to see where specifically that's at, but it's not that 1 carbon bonded to 1 hydrogen, rather that every point's a carbon. That is true. But at those points are the maximum number of hydrogens that they can hold.
Okay.
So in order to satisfy the octet, right, that for this terminal one, that carbon, even though it's not shown, there's 3 hydrogens with that. And then for all the ones in the middle, there's 2 hydrogens to that because they're bonded to 2 carbons. Are we good to go? So like I was saying, because that OH is on the end, you have to show it as such. Ta-da! That's it, magic. Are there any questions? Okay. Let's see. Let's see if you really don't have any questions. something simple. I'll give you 90 seconds, answer it. Draw me something beautiful. In 20 seconds. Okay. Now, admittedly, this one here, I will say, it admittedly is a little more difficult. It does require not just simple counting like with H. Whereas with this one here, you have to be mindful of what's bonded to what and like how many things are actually along the main chain. So for this one, though, you kind of notice that, all right, so at the beginning there, I have what appears to be two CH3s and a CH. Now, if you're not familiar with that now, it's okay. That's why we're in here. Is that usually whenever you see CH3, that indicates that it's going to be a terminal carbon. Because remember, if it's a CH3, that carbon bears 3 hydrogens and so, because it's already bonded to one other carbon. Remember, carbon can't have more than 4 bonds. You understand me? So you know at the beginning, right, for this part here, it's going to be, there's a CH3, and then there's another CH3, because this right there is my CH, at the vertex of those 3 lines. You understand me there? Continuing on, I notice again in parentheses, I see a CH3 followed by a CH. So what that should tell me then is, okay, so at this carbon, so at this carbon here, there's another CH3. Likewise. And then again, because I see another CH3 on the CH, that means I have another CH3 coming off of that. And then this next line goes to the rest of the molecule, which we'll get to in a minute. But at least for the left part here, this is what we have. So this is, all this here is this thing right here. Are there any questions on the first half of this? That's probably the hard part. Go!
So we should put the CH3s before the other ones, like the CH2s and CH.
Before what?
Like before drawing the other ones, like we should draw those first?
I mean, that's a good question. The answer is whatever's easier for you.
Okay.
Personally, like I said, I don't arbitrarily say, oh yeah, start with the CH3s. I just went left to right. And just saw CH3, there's 2 of them with a CH, CH3, so I draw the next one out, CH, CH3, and then the rest of the molecule. Anything else? Go!
I drew that, but upside down.
Oh no!
Is that wrong, or is that just not as good?
I mean, the real answer is it doesn't matter.
Okay.
The answer that I wanted to tell you is that you're a terrible person.
Okay.
Okay? So, like I said before, see up here? Doesn't matter how many of these are drawn, they're all the same. So I know what you're asking, like these are all like flipped around, I assume.
Just literally upside down. Like the 2 CH3s on top were on the bottom, and the CH3 in the middle was on top.
Yeah, no, it's fine.
Okay.
It's fine. The only time that becomes an issue is if you draw something and it, as I like to say, it violates Vesper theory. Like if you drew everything as a straight line, if those little things come off it, that's a problem. But as long as you show here that all the carbons are distinct and you have things that are clearly CH3s, etc., then you're good. Anything else? Go.
So we don't, I see like the CH3 sticking up, and on the one we did before that, we didn't have the CH3 sticking up like that.
I mean, you did. It's right here.
Okay.
Yeah, the terminal, no, it's a good question though. The terminal CH3s, and also, I guess technically as well, what you're saying there, there's a CH3 right here too, as well as that one.
Okay.
So, yeah, it's, the ones on the end stick out, you just, because they're part of the quote-unquote parent chain, if you will, they're not as explicit as, oh, I'm clearly drawing lines out now. But no, it's a good question. Anything else?
Can you define terminal again?
Terminal means at the end. Anything else? Good to go. All right, so for the next bit, I see CO2. Okay, so hopefully we start getting into the familiarity a little bit here that when we see a CO2, that means it's going to be some sort of carboxylic thing. Now again, carboxylic means it's a carbon that bears a double bonded oxygen followed by a singly bonded oxygen. Everyone with me there? And so because of that, remember that because those are oxygens and not, carbons, you actually have to sit down and draw them out. So, this, that, this. Good enough, yeah. And then, fortunately, the rest of it is CH2, CH2, CH3, and so that should just be kind of the standard CH2, CH2, CH3, you're done. So there's that beautiful work of art.
How did you know it was a double bond?
How do I know it's a double bond up? So the reason you know that, I guess, what would you, this is going to sound facetious, but I'm being serious here. What would you like it to be? If you don't want it to be a double bond up, what would you like it to be?
I just couldn't spot it like this quick. Like I would have to.
Well, I mean, of course not. I have a degree in this. Yes, of course I'll be able to spot a little bit quicker than you. That's okay then. That's okay. That's what practice is for. But the reason you know that, let me give you a more better answer than that nonsense one I just rattled off. It has to do, again, if you think of just the way that I always ponder it is, and again, I do this a little bit quicker because I've done this for a while. It has to do with the Lewis structures and the whole octet rule and all that stuff. Because really, when you see CO2, you don't really have a lot of options. You either CCO2, it could be, it's true. I think, let me try to draw all of them. You could have, I guess, this, or you could have this. These lines mean they're bonded to something else. I think that's really it. Yeah, that's really it. That I can think of right this second. And the problem, though, well, hold on, let me be consistent. There we go. Is that the one on the right there's going to be a octet issue, or you'll have formal charges, technically. Whereas for the other one, that CO2, this is, it wouldn't be this, because again, you still have formal charges here. Rather, this form, well, you can't see it, of course, but having a double bond there satisfies the formal charge better than just having a single bond. How are we doing? What do you mean no? What's the matter? This doesn't mean yes, though. What's the matter? Okay? Okay, everyone else okay? Go!
So then for that part, could the double bond go to the other oxygen?
Double bond goes to the other oxygen. Double bond goes to the other oxygen. You mean that?
Yeah.
No. That's a good question, though. Why do I say no to that?
Formal charge.
You got a formal charge issue. Because the one up here, all the formal charges are 0. Spoilers. The formal charge here, there's a positive right there. And that's party foul. Again, remember that there are lone pairs that are supposed to be there, but we don't draw them in over time. But if you need, by the way, I say that, but if you want to take the time right? You want to take the time to draw in all the cute little lone pairs, you're more than welcome to do so. Well, actually, this also has a formal charge too,
Yeah.
so that's a problem.
That's what I was looking at.
Yeah, I don't know. I don't know why alarm's still going off. Class started 30 minutes ago. Right, so if you want to draw those little pairs, that's fine. I'm not going to do it all the time because really the big thing is that, especially when I think we even talk about that next time, is that in the next sections over time we just tell you, they're there, but you have to know that they're there instead of drawing them out. Before that, hold on, I thought I saw another hand over here. Someone, is it you?
Yeah.
Sure. What?
I don't know if this is gonna be in the count, but there's 10 carbons in the formula version, and there's 11 in the one that we wrote.
Yeah, I'm just trying to figure that out. There's like an extra C.
I mean, I could be wrong.
No.
Are we clear?
No.
So you drew an extra line.
No. Every day. Every day. Every day. This is my goddamn credibility here. It's all I do. Just show you that I can't teach. This is terrible. All right, let's try it. All right, this time with feeling. So CH there's CH, there's my CH. So then there's a CH there. Right? There's a CH there. Right? There's a methyl. There's a methyl. I'm about to draw the same thing again.
I think you do a double bond there instead of a single one to the oxygen, right?
Am I stupid?
Because like the C.
I can't even make the it's too early excuse. I cannot even say that right now because it's not. Two CH3s, there's a CH, there's that. CH3, CH, CH3. Did I write it down wrong? Is it possible that I just can't read? That's also possible. I must be an idiot. I'm a legitimate idiot. Okay, hold on. We can do this. We can do this. I'm a grown up. We can figure this out. There's that. There's two substituents. Oh, okay, that might be it. So CH3 is that's that. CH3. No. CH3. C.
Yeah, the first and second carbons are all attached to an extra.
The first and second carbons are all attached.
Yeah, where they come at a point together, there's an extra carbon there.
Right here.
Yeah, there's only 2. Yeah, in the first drawing, we have 3 CHs.
Yeah, there's
1, 2. So I hear all of you leave out of disgust. So CH, there's a CH and there's no CH3s.
See, you got 3 carbons there.
There's 3 carbons, right? And it's those 3 right there.
Yeah.
Then I have a CH that goes here. And then I have
So it's
methyl.
like 2 methyls go to that. That carbon.
Oh, so it's this right here and that.
Yeah.
This, 1, 2, 3.
Yep.
Ah, okay.
Wait, can you show that?
Yeah, can we draw it together as a unit?
No, because, well, here's the thing. The reason that if that's the case, what I see here is this little thing called a typo.
Yeah.
And there might be a typo there. Let's go through it together because clearly the person who's teaching is incompetent. Right, let's try this again. No, forget it. Let's do what we're feeling here. Okay. So if this is true, at the very beginning on the left-hand side, I've got 2 methyls and a CH, right? So I have, you can't see it. I have a methyl, so there we go. Everyone with me there? So I have a methyl and a methyl, there's my CH. Then it's written here, there's another CH, sure. And then there's the problem. Yeah, there's a typo. That's the problem. Yeah, there's the problem. It's a typo. Okay, so yeah, because then we have the CH3s, the CH. Or sorry, there's a CH, right? So that's a CH. Oh my goodness. There's a CH. There's a CH, right? It's those two here. It's this one and this one. Everyone with me there?
Yes.
The problem is, and so here's the other methyl. That's fine. And then the problem is, where does other methyl go? Right? So the other methyl, you would think, oh, it has to go here. And then it would be this with the carbonyl. So there's my CO2. And then 1, 2, 3. And then there's the rest of it. Here's the problem. Here's the problem. You see how it's written here? How that's a CH? How many, so it's referring to that carbon, right? How many bonds are already on that carbon?
4.
Where the hell does the hydrogen go? That's the joke. So I guess technically,
This one would have that formal chart.
it'd probably be more like,
So should the C, so should it be only a C or should there be another CH?
it's whatever you want it to be. It's whatever sort of thing. Oh my Christ in heaven. So for what you all are saying, for what you're saying here is the answer, it really should be this.
Nice.
CH, CH3, 2C, CO2, CH2, CH2, CH3. That's what it would be if you wanted to draw it this way. If you want to draw it this way, this is what it would have to be, was this answer. If it was the other answer, it would be, hold on, give me a moment. The other way would have to be CH32, CH. I guess there's a few ways I could draw this. So CH, CH, CH3, CH, CH3, CO2, CH2, CH2, CH3. So that's 4, and then that top, so get this out of here. Get that out of here. Just forget it. Forget it. Forget it. Get rid of all of that. Okay, so it'd be 4. Boom, 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 boom. Okay, we did it right. All right, so amidst all that nonsense, here's what you got. If you want to go with the one that we talked about before, it actually should look like this. If it's for the bottom one that some of you said, it should look like this. Which one's correct? I have no idea. They're both correct now, but I don't know what Klein was getting at. So there we go. That was fun. Anyone else have any questions? Oh, one that's correct? Well, judging by the time those books seem to look, we got about a 50-50 chance on that. Oh, let me see. Now I have to sit here and actually do them? Oh, damn it. I didn't want that to happen. Okay. Okay, I think this will work. No, I don't know anymore. My confidence is shattered. Damn it. Okay, let's try. We'll just do this one together. Let's do that. That'll be better. Right. Okay. So now let's take a look at this guy. So here I have CH3, CH2, 2 of those. A C followed by a CH2.
Listen.
Okay. So try something out this. So I guess how many, from looking at this first, how many lines am I, or how many carbons am I expected to draw together?
6.
Like in one straight chain. want to be careful how you tell it to me.
4.
At the very least, you know that there's these two over here, right?
Yeah.
So there's two over there, and then there's this thing here. Like I said, there's a couple ways you can do this. So what I'm thinking here is, I know that so I'm actually going to work backwards here. So here is this, right? So there's my carbon and there's my CH2. With me there. And that means off of this left carbon, I should have two of those CH3, CH2 groups. So, well then draw them. 1, 2, 1, 2. Whoops. You see how the structure came about? Because remember, this carbon here, right, this one here, with the three, where the three lines meet, there's the CH2 coming off of it. And if that sounds like a red flag, it should be.
Yeah.
And then there's the CH2, CH3 here, this one on the left, and then the CH2, CH3 up top. Everyone with me there? And what's the red flag?
It's incoming, so it should be CH3.
It actually shouldn't be CH3.
Is there a double bond?
There's a double bond. Ta-da! Magic.
Nice. Oh yeah.
Why is there double?
Because,
There's only
alright,
one.
the reason it has to be a double bond is remember, how many bonds must a carbon have?
4.
4. Before I drew that double bond, how many carbons were there?
3. Oh wait. No.
There were 3 before I drew that double bond, right?
Yeah.
So I mean, at this carbon right here. This carbon right here. And so, assuming this problem is correct as written, which I don't know anymore, but assuming it was, that means it has to have a double bond in there to make sure you have that 4th bond. And I'm going to assume it's correct as written. Ugh. God, today was an adventure. Go! Yes. See, it's a shame I have to do it like this because you guys don't know when I say methyl, ethyl, or propyl, you don't know what the hell I'm talking about. So, and we don't talk about that in chapter 3, but they cover this now. I give up. Anyway, moving on. So, here's what we have. This right here, right? This line here, and I guess subsequently this line. Those are CH3, CH2, CH3, CH2. Everyone with me there? This, right here, is my C. And then this thing at the end is CH2. How are we doing? Okay, this one's actually correct. I'm going to leave this one alone. Don't ask me to change it. I'm not going to. Yes!
This is gonna sound dumb, but can
I'm
you
ready.
backtrack to where, so I followed for the first 3 carbons, and then I got lost. Can you repeat how you did that branch off again?
Oh. Yeah, so first off, no, that was not a dumb question. Let me get this out of the way. I do not believe in there's such a thing being a dumb question. There's either your question is simple, irrelevant, or beyond the scope. You understand what I'm saying by that? So that right there was just more of a simple question. Not irrelevant, not beyond the scope, but definitely not stupid. You understand me? Okay, that's probably the nicest I'm going to sound all semester. Okay, so you're asking me to do the problem again. So you got where the first 3 came from. Good. So you have to understand here. Actually, let me backtrack this further. Whenever that, what does this mean? What does this 2 mean?
There's 2 of them.
There's 2 of that thing in the parentheses, right? So really what we're saying here is, okay, I've got this thing here. I have this thing here. And I have this thing here, and I have this thing here, right? So I have that. And so what that's saying is, okay, so I know I have all that. So when I'm throwing all this together, I know, okay, so the carbon and the CH2, since there's nothing branched to it, it has to be them. Okay, so I think that was okay. And then from there we know, okay, so that means one of these CH3, CH2s is the rest of the, what I'm calling the parent chain, right? It's part of that longest chain. So 1, 2. Everyone with me there? So then, I still have one more CH3, CH2 to accompany 4, and given that I'm supposed to have, as shown, as you all correctly stated, I'm supposed to have 2 of those, well, the only way I can make it have 2 of those and make it look like this would have to go here. Like it can't go to either of those 2, and it can't go to the end, because then it's not what the formula suggests. How are we doing? Any other questions? And I want to do one more, and hopefully the problem's right again. Hold on. All right. I'll try this. I will try it. It looks right. But I felt M was right too. I want you kids to do this one. Just so you guys can practice it without my help, and then also to make sure that it's right. Okay. Right. Hey, probably give you time. So I'll give you 2 minutes. So I'll have to do the last one, though. I would like to push this along. I didn't want to spend an entire class on one section, but thank you, Klein, for allowing that to happen. 1 minute. Ten seconds. Right, okay. So, let me burn through this real quickly here. Well, relatively quickly. Okay, so for this one here, hopefully you didn't get thrown off too much by that CH2OH, but as kind of already alluded to, as mentioned in the previous problem, that whenever you have a grouping, anything in parentheses like that, you know that that thing has to be grouped together. Okay, I'm just going to go left to right here. So I see that carbon that's sitting by itself has a CH3, so I know that for the first 2 carbons, it starts out like that. I don't think that's a problem there. And then on that, I see a Br and a CH2OH. So again, just like what I mentioned above there, that CH2OH means it's going to be its own thing as well as the Br. So what I would expect here would be one thing being the Br, and the other thing being the CH2OH. which look like that. So then from there, I see a CH2 and a CH2. CH2, CH2. And then this time I just see a singly bonded O. Notice it's not a CO2. Right? So no double bond shenanigans. It's just a regular singly bonded oxygen. And then I see CH, CH3. So that means, again, there's another carbon here with a methyl coming, or CH3, you don't know what that is yet. A CH3 coming off of that. And then CH2, CH3 at the end. So understand that, and let me give you the answer first and we'll talk about it. So understand that technically this carbon is bonded to that carbon. That BrCH2OH is coming off of the carbon on the left there. And the reason I know that, there's two reasons. One, remember, bromine can only be monovalent. So it can only bond to one thing, so it has to bond off of the carbon. It isn't going to connect to anything else. And then secondly, that CH2OH, because it's in parentheses, is implying that it's off on itself. Okay? So it's its own thing off of the main chain. So that's why it also gets its own thing, and that's why it's only the carbon going to that CH2 as shown in the arrows. Go! What about it? One more time?
What about the hydrogen bonded to the carbon and the oxygen?
Sorry, you mean this part here?
No.
She means the OC.
OC.
Yeah,
Oh, this thing.
yeah, is that just a
Sorry, is it a what?
Is it implicit?
Implicit in what?
He's asking where you drew it.
Yeah.
Oh, okay. So yeah, for the OCH here, yeah, it's going to be you have to just read it in order because it can't be this. If you can't that's different than what I just drew. And so so the way it would work then is that there's so this CH2 is that CH2. So that means it's going to be bonded to the oxygen, and then just to the rest of the molecule. See, no, it's okay. I'm just stupid for not understanding what you're asking. But okay, it's gonna be okay. Go.
So just for my understanding, whenever you have something in parentheses, that's something that's branch off of the main thing. Almost always.
Yeah, almost always. You'll learn when it's not true. And I'm sure it isn't at some cases. I just can't think of a time right this second. I'm all flustered by the error still. But what you're saying for now when you practice it's not a bad thing to think of. So short answer is yes. Go.
Now when you have the OH branching off of the carbon,
Yeah.
what is that extra line?
What is the extra line? Between the OH and the other carbon? You mean this thing here?
Yeah.
Oh, yeah. So this,
Where's that coming from?
this,
Yeah.
you crying? Jesus. Not that bad. So where that's coming from, that line is the CH2. And then that's the OH. So this thing that I circled is that thing up top, is the thing in parentheses. Go. That is wrong because, so you can't have this. You can't have that because of what I said before. Remember, halogens can only be monovalent. When you put a double bond on it, you're implying it's divalent. And that's a party foul. We don't allow that. Anything else? Go!
Does it matter if the CH2OH is on the top or the bottom?
No.
Okay.
Not yet. Chapter 5. Then it will. Okay, I can take one more, then I have to move on. Fine, be that way. All right. So, good. So for functional groups, one of the things that you're expected to do, I'm curious. Hey, for those of you who took Bio 1, because I haven't taken it in about 20 years, do they still mention functional groups?
Yeah.
They do. They do talk very briefly about organic chemistry still. Excellent. So this shouldn't be a surprise. And this is just one of those things that it's just easy for me just to tell you to know it because I don't feel like writing it out because it's already in your book. Boom. No, I didn't. Okay. Whatever, close enough. That's not all of them, but I think that's all of them. This is going to bother me. I actually have to do this now, or otherwise it's going to bother me. Hold on. Yeah, good enough. Right, so table 2.1. These are all these are not all of them, but these are definitely the functional group's biggest hits. You'll see others as we go along here. But the short of it is, I want you to know all these. Now, what do I mean by that? I'm not asking you to name them per se, well, yet. As you can see here on the right-hand side of each column, they tell you the chapter which they're in. Remember, we only end at chapter 13, so that's that. And we'll talk about how to name those when it becomes relevant. But at the very least, for this exam per se, what I want you to know is I don't know yet. I may ask you, hey, which of these is an alkyne? Which of these is an alkane? Recognize or draw an example of an alkyl halide. Does that make sense? Okay. Really, probably the biggest thing, especially when students start out on this, is differentiating amongst almost everything on the right-hand side there. Yes, there is a difference between aldehydes, ketones, carboxylic acids, acid halides, anhydrides, esters, amides. Yes. Even though they all have a carbonyl moiety to them, moiety being a fancy term for a thing, depending on what's off of that carbonyl means the name changes. Because, in actuality, the chemistry is different. And that's why we put such emphasis on that. How are we doing? Okay, so yeah, if you want to get your flashcard game up, I guess here's the time. Hence why I just put that there. It's like, I'm not even going to write it down, forget it. Okay. Oh, good. So now we can talk about this. So for sections 2.4 and 2.5 where they just talk about lone pairs and carbon atoms with formal charges, because I want to make sure, especially when we start talking about reaction mechanisms and reactions and start going through all that, one thing that's really important is to note what, that's too close, is to note what intermediates we have. And so we need to make sure we understand that. And this is very brief. This isn't going to be too bad here. But when we're talking about anything with, and I'm going to combine 2.4 and 2.5 here. It's talking about both carbons with formal charges and, as I mentioned earlier, identifying lone pairs. We just have to keep in mind what we have. And that, here's kind of the good news, is that, remember, I know I've already asked this about 5 times, but I'll ask it again. How many bonds does carbon have? 4. Very good. So, and you know that because it has 4 bonds, it can have 8 valence electrons, etc., etc. So, we all know, just generally speaking, that if I don't see anything on it, right, if I don't have anything on that, we know that for that carbon right there, that carbon's got 4 bonds as neutral. Not a big deal. But then, you could have this situation here, where you only have 3 bonds on it, and then you see this. Okay, and remember, if you're not sure how that comes out, is that, well, also, some of you can't see it, is that we have 4 bonds, right? Or how many valence electrons does carbon have? 4. It's got 3 bonds to it. What's 4 minus 3?
1.
1. It has a formal charge of positive 1, so we show that by putting a plus. As we're going to see later on, that thing is actually really important because we call that a carbocation. Oppositely, you could have something that looks like this. Now, if there's a negative there instead, how many electrons are around that carbon? 5. Very good. It's not, as you can see here, the way that I've drawn it, it's not explicit, but there is a lone pair there. Okay? And that'll be important later, because we call that thing a carbanion. We don't know the names now, so I'm not writing them down. Class isn't over yet. So just be aware of that, is that if you see a carbon, that later on, this is more for convention's sake, that later on, when we start dealing with intermediates, if you notice a bond, if a carbon only has 3 bonds to it, be suspicious, it's got a positive charge. If you see a carbon that has either a lone pair, or if it has a lone pair on it, be suspicious that it should have a negative charge on it. How we done? Okay. Now I know what some of you are thinking. Well, I don't know this, but I'm going to guess. Some of you may be wondering, wait a minute, this one was missing a carbon before. How did I know that was a double bond? Because I was asking something different. Here I was asking you to draw a neutral structure based off of what's there in front of you. You understand me? Here, I'm just taking that to the next step, is that later on, you may be asked about these intermediates or formal charges on particular atoms. Okay? Again, this is now where organic can become a little, well, really any subject, really. It's now we have to start looking at the subtleties. Now, unfortunately, for some of you, in my opinion, for most of you, the only way to learn the subtleties is just by practice, unfortunately. There's no magical way to do this. So, right. And then, same likewise here, when we're talking about lone pairs, understand it has to do with being able to know the implied formal charges and how many lone pairs are around whatever. So, your book uses oxygen, so I'll just stick with oxygen for now. So, if you have something that looks like that, right? That's ethanol, by the way. So if you look at that oxygen, I did not put a charge on it at all. So right now it looks like that I've only have 2 bonds on that oxygen, right? The carbon and then the hydrogen. But what is implied? How many lone pairs should be on that oxygen? There should be 2. Because right now there's only 2 bonds. That's 2 valence electrons. In order to have the octet, really what this is saying here, it's the same thing as drawing this. Now again, I know this some of you may look at that and be like, well, that's kind of redundant. Yeah, it is. But again, as you're going to see in these practice problems, if you haven't already, we don't always show the dots. We just don't show those lone pairs. We know that they're there already. Again, we're evolving from genpair. And so, we could have, for example, another thing to look out for is you may see something that looks like this. That's a common intermediate. That's an oxygen with a negative on it if you can't see it. So, if that has a negative on it, that means it has a formal charge of -1. It has 1 more electron than it should. So how many than it normally would when it's neutral?
3.
So then, knowing that, how many dots are around that oxygen?
6.
6. 1, 2, 3, 4, 5, 6, and then the bond makes 7. 6 minus 7 is -1 for the formal charge. You understand? Okay, so technically, 1, 2, 3, 4, 5, 6, negative. There we go. And finally, for the sake of completion, as we'll see you might see it in here, I don't know. But, so here we have a carbonyl that has a hydrogen on it, but then it also has a positive charge. So how many lone pairs are missing on that one?
1.
Just 1 lone pair or 2 dots. Because right now you see there's 3 bonds on it, right? And so, 6 minus 3 is 3. But since we have there just a, but since we have only a positive formal charge on it, you imply that there's the 2 dots. How are we doing?
Would you write it as the H away from the O, or would you just write the H next to the O?
Oh, okay. Yeah, that's what you're asking. The question is this. Am I going to write it like that always, or will it be shown like this sometimes? Is that what you're asking?
Yes.
The answer is either. Yeah. I just drew it out the first time and put in faxes on it, but understand that when you have the OH that looks like this, know that the hydrogen is bonded to that oxygen. How we doing? Okay. And likewise, likewise, same thing for nitrogen as well, because, and I cover, carbon, oxygen, and nitrogen because this is the greatest hits as to where you would have these types of issues. Now, nitrogen, though, is interesting because, well, not interesting, it's like the other ones. As you know, oxygen is divalent, carbon is tetravalent. What's nitrogen?
Trivalent.
Trivalent means it only bonds to three things in a neutral sense. So, if I have, I don't know. So if I have something that looks like that, of course, you know that there is, for something that's neutral, you know that there's a lone pair there, right? Whereas if it has 4 bonds to it, you know that because it has 4 bonds to it, that will have a positive, right? And at least for these two, you should be familiar with this because, of course, in Gen Chem, you remember ammonium, right? The ammonium ion, NH4+. And finally, if I see 2 bonds to a nitrogen and has a negative charge on it, that means there are, in fact, 2 lone pairs as well. You understand? Very well. Okay, I mentioned this briefly, and I mentioned this briefly before, but I'll talk about it now since it is in your book, that when we start, especially in Chapter 5, but I mean we'll do it sooner as well, is that you want to make sure you understand the conventions in that you may be asked to draw on your piece of paper, you may be asked to draw a 3-dimensional structure. Right? And as I said already, we do have some conventions for this. I'm not going to go, and I already talked about this. Remember what I said before, is that you have wedges, or what your book calls, I know I used a different term. Your book calls them wedges and dashes. Okay? Wedges, meaning that, we talked about this already, that if they're coming out that if you see a wedge, it's coming out towards you, out of the plane of the page. If it's a dashed or hatched line, it's going away from you. And then if you see a solid line, it's within the plane of the page. Everyone with me there? Now, I'm not going to write these down because I don't want to, because, I'm not here to try to frighten you, but as we'll see later on, throughout the semester and throughout Organic 2, is that there are actually other ways to show, we have conventions for certain forms. And some of these you may have seen in a bio as well, but just to briefly mention. So, you may remember, if you guys remember ever looking at structures of sugars, right? You may have seen something that looks like this or like that, either one. So just, you don't have to write this down now, but we'll get into them. So sometimes we use shorthand here, and that this one on the left is what's called a Fisher projection, in which even though all the lines look to be solid, spoilers, the vertical lines, those vertical bonds are actually going away from you, and all the horizontal lines are actually going towards you. Then we have this thing here, which is called a Hallworth projection, which is usually used for cyclic compounds. Most notably, when you're looking at structures of monosaccharides, it's usually where it's most popular. No, it's not actually planar. It's actually, but it's just for convenience there. And then later on, instead of, because we have this up here, which is a bicyclic compound, which we just draw like this, but most of the time, though, we don't draw it like this, we will draw it like so. And so this, at least structurally, is a similar structure to what's above. Everyone with me there? Again, and don't worry, we'll cross that road again once it becomes more relevant, but I'm just introducing them now, just so you guys, don't get too frightened by it later. Okay. Okay, I got a Gen Chem question for you here. What's resonance?
That's the resonance charge?
You really shouldn't answer the question by using the same word. What is resonance? How does one describe resonance? Say that one more time? Different ways to draw stuff. Okay, we're getting a little closer. What?
Constitutional isomers?
No. I'm actually glad you brought that up. Because that is always a big problem, actually. And that is, constitutional isomers have the same molecular formula, but they differ in how they're structured, right? And how the bonds are connected to each other. Resonance forms are not that. Let me actually, here, I can do you one better. I don't need to ask in generalities, I can just do this. Where'd my markers go? Where'd my other marker go? I'm about to fight somebody. Where'd my marker go? Oh, it's in my pocket, that's fine. That's for resonance. Let me ask you Gen Chem question. You remember that, don't you? Oh, come on, really? Name that. Oh, do not make me put Gen Chem nomenclature on this exam, because I will do it. What's the name of that? No, not nitrogen dioxide. It's got a charge on it. Not nitrous oxide. It's got a charge on it. Begins at N and ends in nitrite.
Nitrate.
Thank you. Yeah, nitrite. It's a nitrite ion, NO2 minus. And so, hopefully you remember that this is not the only way that this could have been drawn. You know what could have happened. You also know it could have been drawn like that, right? And that essentially what it looks like is that it looks like the double bond slid over to the right-hand side. Or it looks like I just flipped the picture. But in reality, I didn't. What happened was, and you remember this from Lewis structures, is that technically the electrons that make up this double bond actually can migrate from one side to the other. Hence making this, or hence making what you see here. And these two things are examples of resonance structures. And you know that these two are fictitious pictures of some hybrid example, in that technically it's neither one of these. What it really is this, where it's not a double bond and a single bond, it's more of like 1.5 bonds. And so it looks something like that. Though you can't tell, those are dotted lines, by the way. So they represent 1.5 bonds. Okay, so hopefully that may have jolted some sort of memory there, because that was Gen Chem. Now notice though, as mentioned earlier, what it is, these are not constitutional isomers. They are the same thing. Okay? The bonds have not broken. Only electrons are shifted around. And so what resonance structures, or when we're talking about resonance, it has to do with this concept. Does your book use the term before I get ahead of myself? Does it? Yes, yes. Does it? Yes, it does. Okay. And so what we're saying here is that these electrons for the nitrite line have delocalized. As in, those electrons are not just stuck on one atom, or they're not only just one bond. Some of those electrons are spread out across, in this case, the entirety of the ion. You understand? And so that's what we're saying here when we have resonance structures, when you have resonance delocalization. And so, as your book already gives you an example for, and I'll go ahead and spend some time on this, we'll give you the answer first. This type right here is we'll learn later on. That thing right there, right, it's what's called an allylic carbocation. A-L-L-Y-L-I-C. You don't have to write it down now, it's okay. But to give you the answer first, this type of intermediate, right, this positive charge, is actually pretty stable. The reason being is that those electrons can resonance delocalize, in which these electrons can move over to satisfy the charge on the one carbon and move it to the other side like so. Everyone with me there? Okay. And so that's what that is. Now let me go into the why here. Why can this happen? Remember, let me just ask you this. Let me try to backtrack a little bit. Let me ask you this. What's the hybridization of those two carbons? The same, that's why I'm asking. That's P2. Very good. Now, remember what I just said. If this carbon here, right, that has the positive charge on it, how many bonds does it have to it? Not one. 3. What's the hybridization of this carbon? It's also sp2. So all of these are sp2. Now, when we're saying something is sp2, it has, three hybridized sp squared orbitals, but also has one unhybridized p orbital, right? Remember that story, I hope. If not, I just told you. So here's the deal with that. Here's why we care. Because, like I said, we already have, and so we have the p orbital. So let's just say the way that I've drawn this, if we're following the picture here, here's my pi bond, right? Sure. And then here's my unhybridized p with the positive charge, or my carbon that has the electron deficient thing. The whole point is this, is that since, and then, let me just draw the other one. Okay, so I just drew the same thing, just with the orbitals. But the whole point is this, and this is what's interesting about resonance, and this is why we even have resonance in the first place, is that if you happen to have unhybridized p orbitals, if you have p orbitals in the same alignment with each other, that the electrons that are in those p orbitals can be localized across the entirety of that space. And so what that means is that technically, which picture is correct, the left or the right? The answer is neither. Rather, what it is that the electrons that make up the p orbital actually go across everything, and the result is you just have you've got partial positives on both ends. That's technically what it is. So again, that's that delocalization. That's what we mean by that, how the electrons can go across more than just a single bond. How are we doing? Go!
Referring to the nitrogen question at the top, would the rightmost one be more stable and more localized?
Oh, that's a good question. So you're asking like if the right one's the most local, the most like.
I guess it's two separate questions, referring to stability first and then localization.
Okay. So the answer to that, I don't remember which way you answered it, so I'll just answer all of it. In regards to like for the nitrite one and also for the bottom one here too, which one's more stable? The answer is neither. They're both the same. Okay. Now in terms of what about that picture on the right? Is that like the actual like localized way to do it? Not really, because what it is, that picture on the right is telling you that we're trying to use Lewis conventions as much as we can to show that the electrons are actually not localized but are spread out. So because you remember from Gen Chem, you've never once had to draw 1.5 bonds. We just kind of briefly talked about it. You know that in Lewis structures they came in 3 flavors: single, double, and triple. And so what we're trying to say here is that because we have those 1.5 bonds, there's no double bond and a single bond, rather 1.5 across thread. Does that make sense? Okay. Anything else? Go!
Those were pi bonds, right?
What?
Those were pi bonds, right?
Yes.
Okay.
Yes. I got 30 seconds. Calm yourself.
Okay, the left side, like the two little drawings that we have, they're actually,
Yeah, so again, for those of you who missed it, why those sp squared is just because, again, it's not written, but there's the double bond, the terminal one has 2 hydrogens on it, and then the other bond makes it 3. The middle one has the double bond and another carbon and then the hydrogen. And then in the end, because it's a carbocation, it only has 3 bonds. All right, now I'm out of time. Thank you so much. Thanks, Charles. We're going until next time. TTFN.